Hello.
Hola, Stefanella.
Hello.
How are you? Sorry that I could not. Do you hear me? Do you hear me?
Yes, I hear you. I have to put the.
Sorry, I could not attend the last lecture.
The link to the lecture are all in the school webpage. There are all the links there.
Okay.
And then you receive the notes, no? The
Yes.
book. Yes, it's okay.
Yeah, thank you.
So Mark should be there. So Nanli, you have now the coordinate.
Yes.
Yes. So Catherine Bonnet, she's a wonderful researcher, and I think she went to China already, but I don't know where. So
Thank you so much.
She's a head of the group, and Frederic also worked with her. They're very productive, and they just do research. They don't have to teach. It's a pure research position. So yeah, it's a nice school. It's a nice school.
Yes, it's a top school in France.
Yeah, I spent there 1.5 years. Very nice environment. Yeah, so I'm sure. Well, when all we will be able to move, so far we are stuck.
Hi, Mark.
Hi.
I'm sorry I joined a little late.
No, fine. So I already put in the YouTube, but today I tried to get organized. I have to remember to start recording, because sometimes I forget.
Yeah, I always forget.
You have to do so many things. This multitask environment is a little bit, well, this has the advantage, you see, we can talk to people from China, there are the Russian, the Italian, so this is the nice part,
It's absolutely amazing, yes.
Imagine.
It probably would have happened anyway, but this COVID accelerated all this incredibly.
Yeah, I think that we have to have a mixture, because it's good to see in person. But
Yeah.
on the other hand, before only people that could afford to travel could access to these things, and now, it's a little bit more people.
Yeah,
People that
some
want
conferences and talks are streamed now, so that's good.
Yeah. You have beautiful weather there.
In Italy?
No, I'm not in Italy.
Oh, you're
here
now. Right. You couldn't make it to Italy, right?
Yes, I'm in space.
We also have very nice weather, but it's an exception, unfortunately, at this time of year. Usually it's cloudy and depressing.
Yeah, well, it seems sunny, so it's nice. Well, Hildeberto, of course, you always have equatorial weather, so too much.
Sometimes a little hot.
Yeah, too much sun, too much light, and maybe the reverse problem.
Well, I wouldn't mind such a problem, to be honest.
Yeah, the first time you see, you have to understand that the Italian, they love it. They grew up with the things that they have to go to the beach and have to get tan. So the first time I went to Recife, I didn't understand people that were hiding from the sun, because it took me a while to see that, it's a different problem, you have to be a little bit careful, So then I learned that you should go for a walk at 6:30, 7 o'clock in the morning, and at 8 o'clock you have to go out with the sunglasses, because the light was, I was not used to that light. So, but at the beginning, yeah.
I read a book, a very nice book. I don't remember the name or the name of the author, but It's written by a trauma doctor. Yeah, I think the book is called Trauma. It's a doctor who worked in the trauma center. Anyway, so he traveled also, he joined the military, and so he was sent to different parts of the world. And he said, after having experienced extreme heat and extreme cold, he came to the firm conclusion that he'd take heat any day. Heat never killed anyone unless, of course, a person is dehydrated, but cold is a different story.
Yeah,
And I completely agree.
yeah.
Thinking when I was a child, in the winter I thought the summer is the best, in the summer I thought winter is the best, but now it's better.
Yeah, I mean, the grass is greener on the other side of the fence, you know, it's always, and it's true that, for example, in Italy, it's very hot. It's very hot, but we didn't have air conditioning. So we know that summer comes with a little bit of sufferance because no air conditioning, you know, that, you know, at night, but, you know, you grow up with this idea that, okay, this is what it comes. And in fact, now in Brazil, I don't have air conditioning in my bedroom. You see, I get used not to have air conditioning. So it's, you know, depends on what your mind is programmed to, you know. But yeah, it's.
When we were in Chicago for a year, we lived the four stations, the four seasons of the year. In summer, we lived in an apartment made of wood, and there was no air conditioning. And when came summer, it was so hot, and then we used to go to the shopping center to spend the afternoon in the air conditioning, and then come to the apartment in the evening. It was really comfortable.
Did you, because I mean, I spent 7 years in Chicago. Did you experience the full winter with -70? Did you have this -70 Fahrenheit?
Yeah, it's quite a difference. In the winter, it's a lot of degrees below zero.
Yeah.
In summer, it's hot like in Rio. So,
yeah. Well, not exactly like in Rio, but you know, maybe you felt because there is no condition.
Rio is 40 degrees. Recife never comes to this.
But it's very humid. It's very humid, and that's make the hair a little bit heavy to compensate. Yeah, but yeah, Chicago is really extreme. You know, it's like. It's like the cold wind. One time I experienced the cold front. So one arm was getting cold and the other was still not cold. I could the transition, you know, because it could be very fast because there are no mountains and it goes quickly.
So the temperature is really good on the average.
Yeah.
Except it's the average. I mean, it goes like this.
Yeah, but you know, anyway. Okay, so people are still waiting for some people to come. So we have part of the PISA contingent waiting for all this traveling. And well, also I was in Toronto. Toronto also is not so so warm. So few experience. Yeah, so Rio, you cannot complain. But no, Rio, it could be very hot. You know, when it's 46, it's a little bit. Try to avoid, if I can, summer area. Anyway, now we are stuck. Let's see. Who knows? You know, yesterday I heard about the fourth doses. I say, what second? I didn't get the third one. People already talk about the fourth one. It seemed a convergent process, you know, where, you know, the time steps are getting closer and you don't know if you're going to converge about this vaccination. Yeah, let's hope that maybe, I don't know, next year. something will come up. Oh, here is the Russians. Actually, we tried to organize a school in Oaxaca, in Mexico, but I don't know. I forgot it's 2022 or 23. I hope it's 23 because 22, I'm a little bit.
Oaxaca is such a nice place.
Yeah, you remember, Mark? It was so nice. Huh?
Yeah, I remember we met, that was what, 2016 probably or so.
Yeah, I forgot. I forgot, I lost track of time. I think it's.
Yeah, I don't do it by counting. I say it by intuition. So
Yeah. Yeah, sometimes. Speaking about cold, my aunt and uncle served for United Nations in the middle of Tibet 1 year for some medical structure. So, and there they didn't have heating at all. It's a little bit difficult in the winter in Tibet without heating. So,
yeah, my friend, his father worked before the Shah. When the Shah of Iran was still in power, he worked in Iran, and he said that some people were so poor they would sleep under the dinner table. They would cover the dinner table with a cloth just to keep warm.
yeah, I guess Eskimo skills. The Eskimo also they use the human body to.
People get used to it to some extent. I read a book. And it's maybe took place. Oh yeah, this is just some guy and some couple decided to spend a year somewhere in Alaska, and lived. There was extreme cold, but the Indians. One woman gave birth to a baby, and the baby was in the snow for a short time, and nothing happened. It was just a standard thing. It's just crazy.
Yeah, because I think the igloo, that within the igloo, they explained to me that is 0 degrees. It doesn't go below.
But
so
it wasn't out in an igloo. It wasn't in the open
outside.
outside,
Yeah.
yes.
Oh,
And I think that unless you, for generations, lived, I think a regular baby would not survive this kind of thing.
Yeah, very strange. No, because it was a French astronomer that explained to me that he went and gave class with the Eskimo, and he was living in a igloo, and then he was explaining, the temp is cold, but it's 0. It doesn't go below 0.
Yeah. Mm-hmm.
So and this was bad when they start building houses with wood, because then it will go below 0 and they need heating, and so it's changed completely. On one hand, you say, okay, you have better inside, but then you have this energy heating problem. So yeah, and it's very fascinating because they don't have trees, but they had vegetable from the fat of the seals. So they still because the seals eventually eat this. So it's a very different ecosystem. Okay, so I think we can start, because I don't know if the other. Okay, we can start. What are you? Is your setup?
Okay,
yeah.
So I will share my screen.
And I'll start recording. Is that
okay.
Okay.
So share.
So I'll start recording. So.
Okay, so I want to. Oh, my screen sharing is disabled.
No, I did it. What?
That's okay.
1 second.
Take your time.
So maybe I able someone else. I able Hildebert. Yes.
Okay, great. iPhone, iPad. Today I'm share. Okay, screen mirroring. Okay, can you see what I have?
Yes, I can see.
Okay, great. So I just opened what I discussed last time. So I was talking about the Aubrey-Mather theory and actually the area preserving maps of the simplest imaginable kind, which actually contain all the information that people understand anyway, more or less. I don't, what I was thinking of doing today was, I think this discussion of the Moser's twist theorem, it maybe is a little bit too technical. And if, although there is a very short proof, obviously a statement as well, of the theorem, and I think maybe it's best if I just give a reference to anyone who would like to know, to a short article which explains how to reduce the question of existence of invariant circles. So we have a twist map that preserves area, and unperturbed map simply rotates circles, geometrical circles, by the angle which smoothly depending on the radius. So it's a twist map. And if you perturb this map by a sufficiently small perturbation, the KAM theorem, Moser's twist theorem, says that many invariant circles survive. That was a huge progress, probably the biggest result in the 20th century in this area in dynamical systems. But I will just give a reference to this, and I will maybe describe something that's fun and kind of entertaining, and at the same time an interesting thing. So this is the lecture 4 that was promised in the outline. I apologize that I kind of crumpled up the KEM theory, but having to make a choice, I would put myself in the place of a listener, and I would probably like to hear this. So here is the thing that kind of amazed me when I was still in graduate school. I learned from, I don't remember who told me this, but anyway, this is an amazing phenomenon, an inverted pendulum that becomes stable, the upside down pendulum. If you vibrate the pivot point of the pendulum, then the pendulum becomes stable if you do vibrations with a sufficiently high frequency. If I can try to share the screen, I will maybe show a video.
You can.
I don't guarantee that it'll work, but I'll try.
If there is an audio, you have also to habilitate the audio at the moment of sharing.
Yes, so I will open. I think that I can share the screen. Let me think. I'm sorry, I'm so bad in multitasking. So I will say share screen and the desktop. I think I should share the desktop. Yes. And I will do this. And I'll do this. Can you see this?
Yes, yes.
Okay, so this is a jigsaw that you will see the blade vibrate in a second. Can you see the video?
Yes, yes, we can.
Okay, great. You see the vibration seems to act, it makes the rod want to align with the direction of vibration. Upside down pendulum is stable. Okay, so that's the stop share. Okay, and now I will share the screen again, but now with the iPad. I wish I was a little faster in this business, but.
No more.
Okay, all right, so here's So here's a puzzling phenomenon. Here is the rod, let's say mass is concentrated at the end point, and the pivot point is vibrating periodically. There is no feedback. It's just down vibration. Why is the pendulum upside down stable? So I can write down the equation of motion. So I can write the equation for theta, for this angle theta. So you don't have to read it, but it's basically length times the second derivative of this theta plus negative g plus amplitude, let's say sine of omega t times theta equals 0. So this is a linearized equation. If I wanted to write the actual nonlinear equation, would be this. So that's the, and when omega is large enough, for some reason, theta will stay bounded. So one can prove this by averaging theory. One can make changes of variables and calculate. For example, in the book of Arnold on differential equations, he takes replaces the sign by the function plus minus 1 with the right rapid frequency, and then you can explicitly calculate what happens to theta after one period of oscillation, and you conclude that the motion is stable, but it still doesn't explain why it happens. And that kind of always bothered me. I knew this thing since graduate school, and one time a graduate student came into my office and he asked me this question: why is the inverted pendulum stable when you vibrate the pivot? And at that moment, it struck me that there is a simple geometrical explanation, which I would like to give. And maybe I should first say how, very briefly, how this problem is treated mathematically before I give this geometrical explanation. So the standard treatment, but I will skip all the technical details and just give the skeleton of the standard treatment, standard approach to proving stability. So you write this system as this equation as a system. So theta dot is omega. Omega is a good, probably I should say, this omega is not the same as that omega. Let me call it V. And V dot is minus, let's say, this is some function Q of t sine theta, or more schematically, if we introduce the vector theta v, so this is the angle and angular velocity. It's a point in the phase plane, right? So we call this x, that's a two-dimensional vector. Then in the end, this equation is just of the form x dot equals to some matrix which depends on time times x. And I don't want to know much about this matrix. Basically, in this case, what is the matrix? 0, 1, minus q, 0. Oh, excuse me. I forgot. I want to linearize this. So I will replace sine theta by theta. So I will, okay, so this is the, this equation just rewritten in a more geometrical way. Okay, so how do we determine stability? Well, we just look at the stroboscopic map or the Poincare map or the time advance map, it's called. We ask what happens to the initial condition. In other words, initial angle, initial velocity, angular velocity. What happens to it after one period? T is the period. In this case, it's 2 pi over omega. Doesn't matter. Okay, so Poincaré, that's given by some matrix called the Floquet matrix. So you can call this Floquet matrix as a stroboscopic map. It simply tells us what happens to any conceivable initial condition after one period. And that F contains all the information about stability. About stability of the pendulum. Why? Because if I want to know what is the angle and what's the angular velocity after many periods, I can, after n periods of oscillation, this is going to be what? It will be the initial information times this matrix to the power n. And so the vector x, in particular, its theta coordinate, which is the angle of the pendulum, is bounded. This vector is bounded by some constant for all n after any number of periods, if and only if this matrix F to the power n is bounded. Okay, so what does that mean? You take a matrix F and you take any power of it. By the way, what do we know about F? We know about F that its determinant is 1. That I should have said that. Determinant of the matrix F equals 1. Why? Well, this is a frictionless system. It's a Hamiltonian system, you could say. Oh, I'm sorry, this is times theta. Oh yeah, I have it. Theta is here. Theta was just written too far. Okay. So this is a Hamiltonian because this system, let's call it 1, is Hamiltonian, which is equivalently in 2 dimensions, its divergence is 0 of this vector field. That is divergence of this vector field. And what's this vector field? It is v comma minus q times theta, times theta. And let's calculate the divergence. So the divergence is the derivative by the first variable of the first coordinate plus the derivative by the second variable, which is v of the second coordinate. You see, v doesn't depend on theta, and theta doesn't depend on v, so the result is 0. So divergence is 0, and therefore the flow in the phase plane is preserving the area, which implies that the determinant of the mapping from time 0 to time t, that mapping preserves area in the plane. So that means the determinant is 1. So to summarize, I want to know the stability of the pendulum. That question is encoded in the property of the matrix F. And stability is equivalent. So the physical concept of stability is equivalent to the linear algebraic concept of the boundedness of the matrix F, whatever that means. You know, the matrix F is bounded for all n, okay? So quick question. So this is a linear algebra question. So keeping in mind that the determinant is 1 and the matrix is 2 by 2, what does it mean geometrically in terms of matrices? A determinant 1 matrix whose powers are bounded. Doesn't matter to what power you take the matrix, You get a bounded matrix. What does it say about the matrix? Well, it's equivalent to saying that the trace of F is no greater than 2. It's not exactly right, because identity matrix has trace 2, and it's bounded, doesn't matter to a power. So maybe I should say more precisely, it's the other way around. It's almost true what I said, but basically, if the trace is less than 2, then the matrix is constant. If the trace equals to 2, then that's a parenthetic remark. If the trace of a matrix then, and the determinant is 1, then F must be either 1, 1, 0 something, or F is 1, 1, 0 something. That's kind of an exceptional case. Let's not waste the time on it. What does it mean geometrically? This is algebraic statement. The trace is less than 2. What does it mean geometrically? All it means is this, that a matrix whose powers are all bounded is an elliptic rotation. In other words, it's similar to the regular rotation. In other words, it keeps ellipses invariant. That means any vector with a tip on the ellipse, if you take the vector x, fx will be on the same ellipse. That's this is equivalent to the statement that the matrix is constant. You see, okay. So this was kind of a quick background on differential equations and linear algebra. Stability of the inverted pendulum is equivalent to boundedness of the matrix, which is called the Floquet matrix also. Better name would be stroboscopic matrix, but stroboscopes probably didn't exist when Floquet lived, so it's called Floquet matrix. Okay, so the standard approach is, for example, how Arnold would do it. He would compute this Floquet matrix, which is a simple exercise. If you have sign replaced by plus minus 1, then you have an explicitly solvable equation, and you replace sine theta by theta, looking at small angle deviations. That's not unreasonable. And so he calculated this matrix explicitly and showed, then you write down the trace and you see that it's less than 2. It doesn't explain anything, but it makes sure it proves it, but doesn't explain it. Okay, so now I would like to give a geometrical explanation. So this thing, if you know all the background, then it takes about a page of calculation, plus the background you need to learn. But here's the proof that one can, well, an explanation of stability, which requires no background in differential equations, is just basically elementary mechanics. So let's look at, this is how the pivot vibrates between these 2 points. And let's look at the mass. Here it is. And so frequency of vibration is huge. So it's going really fast, like in that video. And the amplitude is small. Okay, so this is parenthetic. Okay, so here is kind of a naive argument. So all the mass, let's say, is concentrated here at the tip of the pendulum, okay? And because this frequency is very large, the acceleration is enormous. So this force, let's say this, at this moment, let's say this pivot accelerates up. This compresses the rod. What happened? And it acts with a tremendous force on this. And so I can say, loosely speaking, that this mass moves in the direction of the force. Of course, it's not strictly true. That's what Aristotle would say, that the motion is in the direction of the force. But let's make this as Aristotelian approximation. So let's say that, so approximately, it's actually true because of these two assumptions. Approximately true. Mass moves in the direction of the rod, let's say AB. What does that mean? If that is so, then the mass moves actually in a curve. You see, if you look, imagine you have a bicycle. This is kind of a top view of a bicycle, right? So this is the steering wheel. This is the body. And this is the rear wheel. So the steering wheel is A and the rear wheel is B. If you drive the front wheel back and forth, the rear wheel will travel in a curved path. So this is the tractrix, right? So this is the tractrix. Also the pursuit curve. And to summarize, you see, I'm not, so I'm kind of imposing an artificial constraint on this mass. I'm saying that it moves in the direction that is being pushed. I'm not interfering. So let me impose this constraint that it moves only in that direction. It's a very innocent constraint, right? I'm not interfering with this enormous force that acts like this, right? I'm just channeling it not to move left, right, so to speak, not to turn. But if you have a mass that goes back and forth along a curved path, what's going to happen? It will exert a centrifugal force, right? It will push against you are imposing curved motion on it, so it will resist with the centrifugal force, which is what? This force is proportional to the curvature of the curve times the velocity squared. That's basically the high school formula, which in high school we did this v squared over r, right? The centrifugal force. Well, 1 over r is the curvature. So it's the curvature of the tractrix. Now this is all I need to replace 2 pages of calculation in books like Landau and Lifshitz. Here's the forces. This force is kv squared. I guess I got to the main reason why the pendulum wants to be stable. There is the gravity, of course, which destabilizes, but this force we just discovered, you see what it does. It tries to straighten the thing. So I admit it's not a rigorous argument, but the condition for stability is if this force is greater than what? Than the destabilizing effect of mg, and that is what? Mg sine theta, right? If this is the angle theta, then this is mg sine theta, right? And I should say force is mkv squared, mkv squared. Okay, so what is K? M cancels. What is K? Curvature of the pursuit curve, that's a very short calculation. It turns out to be proportional to the angle divided by the length of the rod plus high order terms. We're looking at small angles. Okay, and sine theta is approximately theta, so this equation becomes masses cancel, so theta over L I keep only the main part of f, right? I just keep this, so I put theta over L, v squared. Now, v is the velocity in this direction, right? That's v. But if the angle is small, then it's approximately the same as the velocity u up to higher order terms, which we explicitly know. If we know the construction of our jigsaw, we know u. So I replace, so this was the curvature. This was curvature. V, I write u squared. And that has to be greater than mass, which was canceled, g theta. I replace sign with theta cancels, and we're finished. So the criterion for stability is u squared. Is okay, I'll just leave it the way it was. Stability criterion is u squared over g over L is greater than g. You see, this calculation didn't take much time. But if you follow, and this calculation doesn't, of course, it's not rigorous, that's its minus, but its plus is it has a geometrical content, and it's short, and it's, for example, the same calculation, even for the piecewise constant acceleration, takes, like I said, about a page in Arnold's book, or maybe two. But this calculation doesn't even care what kind of acceleration you have. You just need a periodic one thing I should say, this should be the average, right? Because I took this picture at a snapshot in time, but I really need to do the average because, you know, and I use smallness of the amplitude because I replaced, I say the curvature pretty much doesn't change much over the different points of this tractrix. Anyway, so this is a non-rigorous argument, but it shows that behind all this complicated algebra, there is a simple geometry hiding. So that's one item I wanted to say, and there's one can analyze what happens if you have a more complicated system, for example, a pendulum with two legs, you know, like a mass or with more. When you vibrate it rapidly, it's known that it is also stable with the rapid enough vibrations. In this case, a similar geometrical picture sits behind the complicated averaging procedure. So that's one thing I wanted to say. So that was just a little snapshot of this. Okay, if there are any questions, I'll be happy to answer. Then I'll go to the next topic. So if not, I will describe, there is another topological explanation of stability, but it's basically relying on a beautiful picture that is due to Gelfand and Lidsky, which I maybe describe because it's really nice to know. It's such a nice and such a basic thing that is just a gem that's worth knowing. So Gelfand, Lidsky, a picture of SL2R. Which is simply the set of all matrices, 2 by 2 matrices with determinant 1. And why do we want to consider these matrices? Because the Floquet matrix is determinant 1. So we want to understand when is the Floquet matrix an elliptic rotation, when is the Floquet matrix of an inverted pendulum is an elliptic rotation, i.e. when is the pendulum stable. Okay, but right now I just want to look at this very, very well focused question. So a determinant of f equals to 1. And here's the theorem, the set, I don't have to, so SL2R, special linear group. Special means determinant is 1, linear group of 2 by 2 matrices with real entries is topologically a solid open torus. The picture is this. So there is a one-to-one correspondence between the points. So this is, in other words, it's a circle cross an open disk. Two-dimensional disk. So to every point in the disk, one can assign a determinant 1 2 by 2 matrix in a continuous way. And let me just draw a picture. Actually, here is the identity matrix, for example, is represented by 1 point in this torus. Minus identity matrix is by another point. Let me redraw it. So it's really beautiful. It's a view of, you can visualize all the matrices at a glance, right? It's so identity matrix is represented by 1 point, minus identity by another point. Where do the matrices, so the matrices which are similar to rotation, so cosine, sine, minus sine cosine. These matrices form a circle, right? As you change theta, this is in one-to-one correspondence to the point cosine sine, right? So if you give a point on a circle, that's this guy, and that determines uniquely in one-to-one a matrix. So one of these matrices is identity. When theta is pi, it's a minus identity. So you see when theta changes, this matrix traces out a circle in the torus, right? What are the matrices that are similar to theta pi over 2 corresponds to this. This is minus pi over 2. This is pi over 2. The matrices that are similar to the 90-degree rotation. So when theta is pi over 2, you get a 90-degree rotation. Matrices similar to it, which you can get by multiplying by a matrix and its inverse on the left and right, that turns out to be a disk. And the same for the matrices that are similar to the minus pi over 2 rotation. Where are all the elliptic matrices? The matrices with traces less than 2. These are stable matrices. This is the name one uses. Stable matrices, which, in other words, which have the trace you know what, I'm going to say, yeah, trace less than 2. Okay, well, the trace could be between 0 and 2 positive. These are here. So I'm shading this. And the matrices with trace less than 2 but negative are here. So it's really a beautiful picture. It just shows how all the matrices sit together. Matrix on the boundary. On the boundary, for example, here, right? This matrix here is similar, is of the form 1, 1, 0, A with positive A. It's a matrix which is a shear, but in some direction, which is, you know, depends on this matrix. Okay, so let me just prove this statement, prove Gelfand-Litsky's theorem that the matrices of determinant 1 form a torus. Okay, let's take any such matrix.
Excuse me, what's T?
D is it's a two-dimensional.
No, T, table, T.
Oh, T, for any T. So T is just a similarity.
Okay.
And one can choose T to have determinant 1 without loss of generality because that, you know, scales out.
Thank you.
For any T determinant 1. Yeah. Okay, so here is the proof that the matrices form a torus. So we can write this F as, this is kind of done with some x plus y, z, plus w, z minus w, x minus y. Okay, so I mean, there are 4 entries in the matrix. So instead of writing x, y, z, w, I write them like this, right? That's certainly, we can do that. Determinant f is, you see what happens now is determinant of f is, this is why I did this. It's x squared minus y squared minus z squared plus w squared, right? And that's equal to 1. I apologize. You know what? Let me do it. Let me do it in a. I mean, one can do it, but like this. But let me redo it. So let's write f instead. Write a polar decomposition of f. In other words, write f as a positive definite matrix, symmetric, and positive definite times the rotation matrix. That's, there is a unique way to write this. So there is a unique P and R, unique such P and R. Why is that so? Because we can actually calculate them. So we can look at the F transposed. I don't yet know. I'm proving that the polar decomposition exists. Assume for a moment that it doesn't. Let's see what P and R must be. So transposed is going to be R transposed P transposed by P is symmetric. So it's the same. And then we can take F times F transposed. Well, that's PR. PR times R transposed P, but R is a rotation matrix and transposed is its inverse, so it's just the identity. So it's P squared. So therefore, okay, so let's choose. So far, I started with something that I don't actually, that I don't know, it's true. But now now choose P to be the positive square root of FF transposed. Well, this is a positive definite matrix. It's also symmetric, of course, because if we take transposed, we get the same thing. We switch, right? So it's a positive definite symmetric matrix. Square root of such matrix can be defined how? So it's a positive definite matrix, and the square root is simply, you diagonalize it and take square root of the diagonal part, and that's what we mean by the square root. So more precisely, write F transposed as, by diagonalizing, write T times diagonal matrix times T, right? And diagonal matrix is with positive guys. These are positive. Why are these positive? Because FFT is a positive definite matrix. Because, right, is positive because if we take FF transposed, apply to any vector X and take the dot product of with X, we get F transposed X dotted with F transposed X, right? And F is non-singular, so this is strictly positive if X is non-zero vector. If X is a non-zero vector. So therefore, eigenvalues have to be positive. And so then we define square root of FF transposed, as simply T inverse square root of the diagonal matrix, which is simply what matrix with square roots on the diagonal T. Then T inverse diagonal T square. I want to show that this is a genuine square root, so I have to square this, which I'm doing, and I want to show that we get FF transpose. So let's see, we get T inverse square root of diagonal times T multiplied by the same thing. And so T and T inverse produce identity, and D times D square root just produces D, because square root of D is just the matrix with roots of lambda on the diagonal. So it's T inverse D T, and that is indeed FF transposed. Okay, so indeed this this qualifies as a genuine square root. In summary, so I produced P, and then you can write R here, write R as F times P inverse on the left, P inverse times F. And it's a simple matter, which is not very instructive, to show that R is indeed a rotation matrix. In other words, that R satisfies R transposed R is identity. Okay, so coming back to the starting point, we took any matrix F, we wrote it as a positive definite times the rotation. Geometrically, what does it mean? That any matrix can be You see, what's the geometrical meaning of this polar decomposition? It says that every matrix, if you rotate let's see, so if you apply a matrix and then you rotate appropriately, then what you get is a hyperbolic rotation. Okay, anyway, so now, this is determinant 1 by definition. That's what we start with. This is a rotation matrix, therefore its determinant is 1. Hence, P has determinant 1. The positive definite matrix has determinant 1. So, but P is a symmetric matrix, which means I can write it as X, Y. It's symmetric, so Y is here too. And here I write X plus Z, and I write X minus Z. So positive definite. And determinant of P is 1. Therefore, X squared minus Z squared minus Y squared equals to 1. Which means that X is square root, well, X squared, let's say, square root of 1 plus Y squared plus Z squared. So that's 1, sorry, X, not X squared. And furthermore, now the question is X positive? Could X, I didn't write plus or minus, right? I solved this for X, but I only wrote with a plus. What right did I have to do that? I had the right to do that because I said P is positive definite. That I have not used yet. I only used the determinant equal 1, but I did not use P positive. So P is positive definite matrix implies that the trace of P is positive. But the trace of P is what? It's 2x. So that's why I did not put a minus. Okay, so to summarize, the matrix P, for the matrix P, it's of this form. And if you know Z and Y, X is uniquely computed, right? Y and Z determine everything, determine X and therefore the whole matrix, right? P is parametrized by Y and Z, which is a point in R2. So in other words, we have a one-to-one correspondence between the plane, the points in the plane, and matrices P, positive definite matrices of determinant 1. That's kind of a nice fact to know in principle, right? The set of all positive definite matrices of determinant 1 is topologically just R2. And R2 is the same as an open unit disk, okay? So P is topologically the same, the set of matrices P is the same as the open unit disk. Okay, now, and the rotation matrices are the set of all rotation matrices, as I already mentioned, is topologically a circle, because these are of the form cosine, sine, minus sine, cosine. And so, therefore, we conclude that the set of matrices PR, which is the set of all matrices F in SL2R, this set of matrices is topologically just the product of the circle with the unit disk in the plane, and that proves the theorem.
Is there a similar result when the determinant is -1?
Oh, it's a good question. I never thought of this. It's got to be, because these maps can be realized as a composition of the ones we just discussed and the reflection. So yes, I think so.
Okay, thanks.
Yeah, thank you. That's a good question. I never thought of this question. Okay, so this is a beautiful thing. Now, how do the stable matrices, how do we explain the picture that I drew? I claim that the elliptic matrices, the ones that are of the form,
But 1 second, but they will not be identity, you know?
I'm sorry?
If it's -1, they will not include the identity, no? See? Is it the same or not?
I'm sorry, I apologize. Let me turn my sound a little louder.
No, I say if it's the question of Giulio, if it's -1, it can include the identity.
Of course, yes.
Right. So
So
there will be some matrix. I guess you multiply all of these matrices by the reflection. So it will not be identity, it will be the matrix 1 minus 1 on the diagonal.
1 minus 1. Yeah, this is simple. No.
Yeah, 1 minus 1 and the other one
See.
minus 1, 1. So just multiply the whole picture by a reflection, I think. That's probably true. Well, but they don't form, they don't form a group, I guess. When you multiply to, then the determinant.
No, because yes, because I was thinking to the general group, including also the matrices with -1. That's why.
Yeah.
Yeah.
Okay.
Okay, but anyway,
Yeah.
thanks.
Okay, so how does this stable set sit in this? So let me this is a simple exercise to show that the set of elliptic matrices looks like this. In other words, if you look at the matrices which of the form P times, so take the matrix of the form P R, which is X plus Y, Z, X minus Y, times cosine sine minus sine cosine. And if you ask for fixed theta, that means you fix your location on the torus, right? You fix theta because theta is measuring this angle, right? Because we agree that R, the rotation matrix, is parametrizing the length along the torus. So I want to show that as theta increases, this range of stable matrices becomes smaller. Let me not do this, but basically you can fix theta and see for which X, Y, Z, which are not independent, of course. X is really, I don't have to list because it's dependent on Y and Z, right? Like we said before, here's this entry X is determined by the other two guys, Y and Z, by virtue of determinant being 1. Anyway, so fix theta, and you will see that for which y and z, the trace of PR is less than 2. It turns out that as theta increases, the range y and z, kind of a circle that y and z describes, shrinks. Shrinks as well, actually, let's see, opens. As you travel starting from identity, it opens. You see, if you start with identity, it's easy to perturb identity to violate stability. If you don't, but if the matrix, it turns out, okay, I am saying too much. Let me just say one thing. Instead of just one little item. So here's elliptic matrices, the set of elliptic matrices obstructs the torus So in other words, if you take a matrix that whose PR, whose rotational part goes around the torus, that matrix must pass through stable set. So this is what I'm claiming. And the proof is trivial. Any matrix PR with R a 90-degree rotation, in other words, 0, 1, minus 1, 0, is elliptic, i.e. it has a trace less than 2, i.e. PR is similar to rotation. So it's some matrix T times this rotation by 90 degrees times T. So it doesn't matter how many times you iterate, what power you take, so it's bounded, right? Because PR to any power is just going to be the same thing, T inverse T times a rotation by pi over 2 times n. And that, of course, is bounded. This matrix R is just either identity or minus identity, or, you know, it only takes on 4 values. Okay, so here's a very simple proof. So it's just an elementary linear algebra. I want to show that take any positive definite matrix P and a rotation by 90 degrees, it's a stable matrix. So let's say V1 and V2, these are eigenvalues of P. And they're orthogonal because P is symmetric. And furthermore, lambda1, the corresponding eigenvalues, and lambda2 is a determinant of P, right? And that's 1. So the eigenvalues are reciprocal. So let's see what happens. What does PR, let's apply PR to eigenvalue V1. Well, R, you see, R is the rotation by 90 degrees, right? So R V1 is V2, so it's PV2. So that's lambda 2 V2. So we discover that one application of PR to the first eigenvalue gives you the second eigenvalue times, sorry, second eigenvector times the eigenvalue. Let's do this again. Let's apply PR to lambda 2 V2. See, I took V1, applied PR to it, and then I apply PR to the result again. So that's lambda 2. Rotation of V2 gives minus V1, right? I factor lambda 2. P applied to V2 is minus V1. And there is P in front. And P applied to V1 is lambda 1 V1. And that's 1. So the upshot is, if we apply the matrix PR to V1 2 times, we get V1 with a minus sign. The same, of course, is going to be true for V2 because my argument is symmetric. I could have chosen V2. So we conclude that PR squared is minus identity. And therefore, all powers of PR are bounded. So PR is an elliptic matrix. So that means that when theta, you change a matrix and its theta changes, the moment theta is equal to pi over 2, the matrix has to be stable. We don't know where exactly is this matrix in the disk, but we do know that it is stable. So any matrix in this disk is stable. Okay, so that's the end of the discussion of the SL2R. And let me just say in a couple of minutes, what does this have to do with the pendulum? I remember I was walking down the street and I stumbled on a piece of broken concrete, and then I realized at that instant that this picture that I just described explains why an inverted pendulum has to be stable. So let's look at the equation of the pendulum, which I write as x dot equals to the matrix, and it's linearized. So x was the angle and the angular velocity of the pendulum, and a is the matrix. It doesn't really matter, 0, 1 minus q, 0, where q is the coefficient of x in the differential equation. The differential equation was this. Let me not write it, it doesn't matter. Okay, so we can write x of t, this is the vector at time t in the phase plane, right? So we have the phase plane x, we have the phase plane x, whose coordinates are the angle of the pendulum and the angular velocity. And we can write x of t is the fundamental solution matrix at time t times initial condition. So in other words, if I start with the vector x of 0 and wait time t, this vector x of 0 ends up in a new place, x of t, and the matrix F is what sends it to x of t. So, and let me do one more step. So I can decompose F as determinant 1 for all time because the flow is preserving area. So I can write it as a positive definite matrix times a rotation matrix times the initial vector. And this is x of t. This equation links physics with geometry. On the left-hand side, we have physics. We have the angle, we have the vector x, whose horizontal coordinate is just the angle of the pendulum. So for example, if the pendulum, imagine what happens when the pivot of the jigsaw accelerates down. It feels to the pendulum like the gravity points up. And if the pendulum was very short, which is not the case in this experiment, but if you imagine the pendulum being very short, then it will oscillate many times on the downstroke, right? The short pendulum will oscillate down many times while the acceleration is down at the pivot point, right? What does it mean? So that's a physical observation. So as the length of the pendulum which I choose to be a parameter, becomes small, x of t oscillates many times during the period of one up and down motion of the jigsaw, right? Of course, it happens on the downward acceleration. So what does that mean? So here is this vector goes, when the pendulum oscillates, so not x of t, theta of t, the angle oscillates. But that, what does it mean in the phase plane? If theta goes left or right many times, that really means that the vector rotated many times. X of t rotates many times during this period, right? So during one period, the vector in the phase plane rotates many times, this vector. Well, what does it say? Here is a vector and these are matrices. P is a positive definite matrix, which notice that a positive definite matrix, what does it do? It simply stretches along one direction and shrinks along another. So any vector stays in its quadrant. When you do this, the vector is confined to a quadrant. So positive definite matrix cannot rotate anything by more than 90 degrees, not even by 90. So all the rotation is due to R. That's the key link. So we, from physical understanding that the pendulum does many oscillations, we know that the matrix, the rotational component of the Floquet matrix, rotates many, many times during one period. So that means, let's look now at this matrix PR. It lives in our torus. It starts as an identity matrix. And as time goes from 0 to a period, this matrix did many, many, many revolutions and ended somewhere. So this is a matrix PR at time t, at the period t, right? And the number of rotations is big. Now what's going to happen when I make, so far I had fixed the length of the pendulum, but now let me make the length of the pendulum shorter. This curve that I just drew, this path of the matrix, will become, will gain more and more rotations around the torus, right? So in other words, this point, this matrix PR, as a function of the length of the pendulum, will itself go, the snake will become longer and longer as the pendulum gets shorter and shorter. So this point will have to execute infinitely many rotations as the length of the pendulum goes down to 0, and therefore there is an infinite sequence of lengths for which this matrix lives in the shaded set of elliptic matrices. So this proves that there exists a sequence of intervals, so I'll just draw a picture, length L, and there is a sequence of intervals of length for which the pendulum is stable. Admittedly, it's not that parameter range which the experiment shows, but at least it shows that topologically, just a topological argument. The only analytical part of this argument is the need to show that the pendulum oscillates many times, but that's a very simple thing by comparison with a constant acceleration. It's trivial to show. Okay, so yeah, I think I'll stop here. It's probably enough. I wanted to describe, but I don't have the time, and some open questions, for example, if you look at the different but related problem of motion of a particle in a rotating saddle. For example, if you have a, just to give a flavor, if you imagine an elongated asteroid, no vibration, but now rapid rotation. So this asteroid is elongated and rotates very fast. And if you look at the particle of dust somewhere that feels the gravitational oscillating gravitational field of this asteroid, there is a remarkable thing that I don't think anyone understands. It looks like if you average the motion of this dust particle, it is subject to a fictitious magnetic force. Of course, it's not magnetic, but mathematically, it's the force that's perpendicular to the velocity of the particle. So the particle kind of jiggles because the gravitational field jiggles, and but there is kind of an averaged motion of the particle. If you kind of eliminate these jiggles by change of variables, so there is an average motion, and that average motion is like a fictitious particle, which is a subject to this quasi-magnetic force, so the force perpendicular to the velocity. So, and that's basically done by blind calculation, but I don't understand geometrical reason for it. There's got to be, I think, but I couldn't figure it out. So I'll stop here.
Thank you very much, Mark. I was saying that this lecture are a philosophy of mathematics. They make you think about it. Thank you. Thank you very much. So we would like to thank you for all the 4 lectures. So please open the microphone to thank you. Mark with me. Thank you.
Thank you very much for inviting me.
No, it's a luxury. It's a luxury. And so if people want to ask some questions, please get some questions.
This result about the asteroid, I was interested. You know, yeah. Here we are this group of celestial mechanics, so when you mention asteroid, yeah. Is it a paper published?
It's we have an article with it's not formulated in terms of an asteroid, but it's basically any any potential a potential. Yeah, we have an article with Graham Cox, which says this, that if you have a rotating, doesn't have to be rotating, but for example, rotating potential for a field, potential force, then it gives rise to this, yeah.
Give us the reference.
Yeah, I'll be happy to give you the reference. I'll send you the reference. So I'll send it to Stefanella.
Yes, I understand.
I'm just writing it down so I don't forget.
I just want to say to the people of Pisa that we had Angel Jorba giving some astrodynamics.
Yes. You had or you will have? Sorry.
No, we had, but the videos, and if you want, I can send you the slides. The videos are on the webpage of the school.
Okay, thanks. Yes, we know him quite well.
Invariant manifold.
Very manifold, yes. Of course.
And so I can send you the slides.
Thanks.
But
yes.
The videos are there, and also Deberto give a course also last on stability. So we have all the material there.
Thanks, Stefanella.
No, nothing. Actually, maybe next year some of you would like to speak in our course, because it's a circulating school. So Andrea Venturelli said
Clara and Irene here desire to no, I'm joking with them because they are here, the same office as mine.
Andrea Venturelli said that they might give a course on variational method, but
Andrea, yes, I know Andrea.
Yeah, let's see if he confirms. In principle, maybe next year he will give a course on variational.
Yes, I know also Ezequiel Maderna.
Yeah, Maderna, yes, I visit him. Yeah, okay, so more questions for Mark? Since
Mark, I would like to comment. I liked the lecture. I lost the last one, the previous one, but the 3 lectures that I watched, I found very interesting. And today, especially the exposition about the Gelfand-Lidske way of finding the stable matrices with that pinched torus. I enjoyed it, and I liked it very much. So thank you for the good lecture that you have given it to us, and that's
Thank
it.
you very much. It's really good to see you again. Yeah.
Yeah, very nice geometrical picture. I totally agree with the developer.
Yes, I also completely agree. I was very interested about this last part also.
Yeah, I think it should probably be in many books somehow. For some reason,
I never seen, but if you have a reference, I would be happy. You know, it could be interesting to motivate.
Yeah, I will see. I don't remember. Yeah, I must have it. I'll try to find it.
I think the original paper by Gelfand-Lidske has this picture.
That's right. That's where I learned it from.
Mm-hmm.
Do you have the article? Well, if you can send me the article.
I probably have the reference to that article in one of my.
There is it's a Russian, but I think there is a English version of this article. I guess I can get it, and if I get it, I send to you.
Thank you, because I remember once I had to review a Russian paper and the reference were in Russian, and it took me a while to Google Translate and understand something. My Russian is not so good, but eventually I could translate the alphabet, but if it's in English, it's better.
The Gelfand-Lidske paper is translated into the Translations of American Mathematical Society. I don't remember the year, but in the 50s.
But if someone has it, please send it, please.
Okay.
Yeah, I will look for it. When I was in graduate school, we had to take an exam in 2 languages, so you could choose between German, French, and Russian. And so I chose French and Russian. And the funny thing is I spoke Russian better than anybody else at Courant, obviously. But I think I was the first Russian student there. But the funny thing is they gave me an article in Russian to translate. I think they just wanted the translation. I don't think they wanted to test if I know Russian, because I don't think anyone doubted that. I think they just wanted the translation.
You know, in Italy, when I started, we had to choose the first year some languages, and we had a teacher teaching Russian. Yes, the first year, theoretical physics. But we had, you know, it was first year, and we had analysis 6 hours, and physics 1 and geometry and so on. And I realized that learning Russian was equally demanding. So I couldn't go beyond 4 or 5 classes because, you know, already to learn the alphabet was hard at the beginning. So yeah.
The French was very easy. If you speak any of the Latin languages or even English, French was really simple.
Yeah. Well, you know, phonetically, not so much.
Phonetically, yes, maybe it's not so much.
I was very happy about some special classes at the Sorbonne. They do just phonetic classes, so that really helped me. By the way,
I once heard a lecture by a well-known mathematician in French. I was in Paris and I went to hear his lecture, and I never studied French except for the 2 days before my language exam. And I understood almost everything he said because his accent was so bad. He spoke basically, I think he spoke Russian, but he used French words. I'm sorry?
No, I think it was an internal message.
Oh, okay.
So sorry. Sorry, I'm sorry.
Oh, that's completely okay.
When I took my doctorate degree. Usually, people from Brazil used to choose German and French. I decided to choose German, Russian and French. Then I took some courses in Russian and could pass the exam. And later on, this helped me very much because it's quite a rich literature. And that decision to take the Russian exam in my qualifying was very important for the future.
Yeah, you also translate, no? You do translate Marquez's work?
Yeah,
no?
I can translate, but not speak.
Yeah. Yeah, no, I wish when I went to Russia, I tried 10 days, but it was not enough. I should study more. Well, next time maybe. So thank you very much.
Thank you very much.
And just to advertise, next course will be Thomas Alarcon from the CRM of Barcelona. We'll talk about stochastic equation with some application into biology, I think. And that will be at the end of November. And that will be the last course of this semester. But then we will be next semester again, as I say, I hope Andrea Venturelli again about celestial mechanics. So we try to keep going, covering different area. Okay, so thank you very much, Mark. Thank you for the wonderful journey. So bye-bye, everyone.
It was nice to meet you.
Bye-bye, Roberto. Good to see you.
Bye, Stefanella.
Bye-bye.
Bye-bye, Bruno.
Thanks to everyone. Thanks.
And think of Julia about a course also.
I will think.
Okay.
Thank
Ciao,
you.
pessoal.